In the previous lecture, we started with analyzing the quarter wave transformer from a time domain perspective, and we had sort of abruptly paused in the middle. So, assuming that you are familiar with the analysis that we started, we had essentially derived these two quantities for this arrangement. Z0 line, there's a Z1 line which is the quarter wave transformer, and there's a load ZL which is real. So there was this reflection coefficient here gamma 0 and a transmission coefficient that is T0. We had proved that at time t equal to T0, that is at the time when the wave going right hits the boundary, that is x equal to 0, and this is positive x. At this time, we had said that T0 is equal to 1 plus gamma 0, and we had shown that gamma 0 is this reflection coefficient between Z1 and Z0, that is Z1 minus Z0 divided by Z1 plus Z0. Similarly, T0, just by applying this, turns out to be 2Z1 divided by Z1 plus Z0. Now, so far, whatever has happened, let us try to denote that by means of a bounce diagram, which we already know how to work with. So let us say this is the point where x is 0 and this is the load. Suppose from source the wave starts at time t equal to 0 and it hits the boundary at time t equal to T0. So let's put the time axis over here. So let's say this is T0. So effectively what we are seeing is that there's a reflection coefficient gamma 0 and a transmission coefficient that is gamma 0. And after some time, this wave continues to travel and hit the load. And the time when it happens, we had proved that this time is T0 plus T1. So here, the reflection coefficient is the load reflection coefficient gamma L, and so on. So which then again comes back over here. Now it undergoes a transmission, let's call it as T1, and another reflection coefficient gamma 1, and so on. So what we are seeing, that when we are looking into this junction, we expect to see the reflection as a single quantity. But that's not the case. Effectively, we are seeing a multitude of waves. And if I draw these more, you will see that there are more reflections. So effectively, what the outgoing wave that is seen as the reflected wave from Z1 into Z0 is seen as a superposition of many of these waves. So that's what it is. So the question is, this happens at what time? This time is T0 plus 2T1. So let us sort of draw this even longer. Let us now look at only the Z1 section. So when this goes, it hits over here. This is at time t0 plus 3t1. There's one more reflection coefficient, same as load reflection, that is gamma L, and that strikes back. And you have again some T2 and gamma 2. Say, well, it will not be T2 and gamma 2. In fact, it will be T1 and gamma 1 itself, because these are repetitive phenomena. So same wave is coming back. So T1 and gamma 1. So no need to introduce any additional variable and make life difficult, because just the way this wave underwent T1 and gamma 1, even this wave would undergo T1 and gamma 1, which is opposite to this gamma 0 and T0. This is T0, just be careful. So now, what is the reflection coefficient due to this first reflection? The first reflection coefficient is gamma 0. Now let us look at the time T0 plus 2t1 and write down what is the second reflection coefficient. Now it is not so easy. We have to see what gives rise to this wave. This wave comes because of this incident wave, which undergoes, let us say it has magnitude of 1. It undergoes a transmission coefficient T0, a reflection coefficient gamma L, and another transmission coefficient T1 at this junction. So therefore there are three coefficients which are playing a role: T0, gamma L, and T1. So therefore, because there are multiple coefficients of the same wave, they will all get multiplied. And the second reflection coefficient will be T1 times gamma L times T0. Likewise over here, at T0 plus 4T1, there will be the third reflection coefficient. That will be what? Again, you need to trace from here to here. T0, gamma L. Now T1 will not play a role because we have to look at this wave. T0, gamma L, gamma 1, again gamma L, and again T1. T1 over here. This gamma 1 will not play any role. So let's write this down. T0 times gamma L times gamma 1 times gamma L, which will make it gamma L square, times T1. Yes, I think this is fine. Right. So likewise, there will be multiple such reflection coefficients. So now let us put one more constraint. Let us say that this length is some lambda 0 by 4. Then what? If I say that this wave or this length of this matching transformer is some lambda 0 by 4, and say that at t equal to t0 there is a voltage wave, let's call it as V1, that is some V0 cos omega 0 t. This is the wave that hits the point x equal to 0, that's the boundary. This is Vi. So what will be the first reflection, the first reflected wave? So the first reflection coefficient, as you know, is gamma 0. Then I can say Vr due to the first reflection, that will be gamma 0 times Vi, which is gamma 0 V0 cos omega 0 t. Now, after it goes over here and comes back, this is at time t0 plus 2t1. This is the second reflection coefficient. So in that case, I can say Vr due to second reflection coefficient. How much would that be? That will be the net reflection coefficient multiplied by the input voltage. We just found that out. So we found out that the reflection coefficient for the second time is T1 gamma L T0. That is T1 times the voltage. Now which voltage? Will it be V0 cos omega 0 t? No, because we are merely talking about the coefficients at either the boundary or at the load end. We are not talking anything about what goes on while the wave is traveling. So therefore we have not incorporated the time phase information of the wave. So if the wave goes from here to here, that means I said that the length is lambda 0 by 4. That means every time it travels from this point to this point or this point to this point, each way the phase shift theta is beta L, that is 2 pi by, let's say, lambda 0 into lambda 0 by 4, which is pi by 2. So going here and coming back means pi by 2 plus pi by 2, which makes the phase 180 degrees or pi radians line. So therefore the voltage will be V0 cos omega 0 t minus pi. So using the trigonometric identities, this will become a minus cos. So what we get is minus T1 gamma L T0 V0 cos omega 0 t. Likewise, for the third reflection at T0 plus 4T1 due to third reflection coefficient, what will it be? Now it will be 180 plus 180. So that's 360. So there is no phase difference. So therefore, now we can directly put this coefficient and multiply it with the input. That is T0 gamma L square gamma 1 T1. So that will be T0 gamma L square gamma 1 T1 times V0 cos omega 0 t, and so on. So as you know, the reflected wave that is seen by the left side looking into this junction is the superposition of all of these reflected waves. So what would that be? That would be, let's take V0 cos omega 0 t as common. So it's a total reflected wave at the junction. V0 cos omega 0 t, and inside all these coefficients will come, that is gamma 0 minus T1 gamma L T0 plus T0 gamma L square gamma 1 T1, and so on. So this is the total reflected wave. What's the incident wave? incident wave is this. So we can define the total reflection coefficient as the total reflected wave divided by the total incident wave. So I will say net reflection coefficient at the junction, that is total reflected wave or outgoing, I will not say outgoing, I will say total reflected or backward wave divided by the incident wave. So how much would that be? That is nothing but the quantity in this bracket. Let's say this is gamma. This becomes gamma 0 minus T1 gamma L T0 plus T0 gamma L square gamma 1 T1 and so on. So every alternate term will be positive, every alternate term will be negative. So you can take a look at all these terms except the first one and notice something very similar. You can effectively take this term common out of all of the remaining terms and show that this essentially is a geometric progression. This becomes gamma 0 minus T1 gamma L T0. There are infinite number of reflections and the geometric term is minus gamma 1 gamma L whole raised to n. You can take one more term from the bounce diagram and convince that this is indeed the case. Right? Now, what can we say about this quantity? The reflection coefficient magnitude can never exceed 1 and in this case it will always be less than 1. So this product, the mod of gamma 1 gamma L, will be less than 1 always. So this geometric progression would essentially reduce to this 1 minus this, that is the numerator will stay as this term T1 gamma L T0 divided by 1 plus gamma 1 gamma L. Right? So to have matching, we need what? Gamma should be equal to 0. So that means this whole term should be equal to 0. So simplify. So what we will get? Gamma 0 plus gamma 0 gamma 1 gamma L, look at only the numerator, minus T1 gamma L T0 should be 0. What is gamma 0? Let's put all those that we derived. So gamma 0 is Z1 minus Z0 divided by Z1 plus Z0. What about T1? What about T1? T1 will be 1 plus gamma 1. You can prove this. T1 is 1 plus gamma 1. It is just an extension of T0, which is 1 plus gamma 0. So gamma 1 is the opposite or negative of gamma 0. T0 is 1 plus gamma 0 and T1 will also be T1 would not be negative, but rather T1 will be 1 plus gamma 1. So that is 1 minus gamma 0. So let's put these. Gamma 0 plus minus T1 T0 gamma L is 0. So gamma 0 is Z1 minus Z0 divided by Z1 plus Z0 plus Z1 minus Z0 divided by Z1 plus Z0. Gamma 1 is just the opposite of this. So you can actually say minus with a square. Gamma L is ZL minus Z1 divided by ZL plus Z1 minus T1 T1 would be what? 2Z0 divided by Z0 plus Z1. T0 is 2Z1 divided by Z0 plus Z1, and gamma L is this ZL minus Z1 divided by ZL plus Z1. This should be equal to 0, right? So this is a pretty long expression. So we can definitely take out some terms common, and stepwise if you simplify, you will see that you will obtain Z1 as a function of Z0 and Z1, and you will see that Z1 will be equal to Z0 times ZL, and this is exactly the condition that we derived in the previous lecture, where we analyzed the quarter wave transformer but from an impedance transformation angle. And in this particular lecture, as a continuation of the discussion of the previous lecture, we saw that using the time domain analysis or the transient analysis, we will pretty much end up with the same solution, but using two different techniques. Now, in the previous lecture, we discussed that one drawback of a quarter wave transformer or the QWT. We said that if the length of the line is fixed, then there exists only one wavelength where the length of that quarter wave transformer corresponds to lambda by 4. That means if you extend lambda into frequency, you can say that there exists only one frequency or a single wave having a unique frequency where the quarter wave transformer will act like a matching transformer, proper matching transformer. So let us look at this in more detail. Suppose I have a source that's connected to some transmission line Z0, which is connected to another matching transformer, which will ultimately be a quarter wave. This is Z1, and the load impedance is obviously real, that is ZL. Let us say the electrical length of this section is some theta, which is beta L, where L is the length of the line. So let us say the impedance looking into this matching section is some Zin. So what is Zin? We have proved this already without applying a specific value of theta. That is nothing but Z1 ZL plus JZ1 tan theta divided by Z1 plus JZL tan theta. Right? Later you can put theta as pi by 2 and you will arrive at the relation that Z1 should be the geometric mean of Z0 and ZL, which is precisely what we obtained in the previous lecture. But this is not what we are doing right now. What we are doing is we have to see how this behaves as a function of frequency. So therefore, let's fix the length of the line. Say L equals some L0, which is lambda 0 by 4. So therefore, we can say theta is beta times L. L is lambda 0 by 4. And if you assume there is a wave of unknown wavelength lambda, which is traveling along the line, lambda may or may not be equal to lambda 0. This is what we can write. This is pi lambda 0 divided by 2 lambda. So if I now want to express this quantity using frequency and not wavelength, so then I can say that if the wave has velocity v, which is some f0 times lambda 0 in case the wavelength is lambda 0, which is also equal to f lambda, where f is unknown, lambda is unknown, but it is of the same type of signal, which is an electromagnetic wave. So therefore, if you simply put lambda 0 as v by f0 and lambda as v by f, you will get this becomes equal to pi f by 2 f0. Effectively the reverse. So now, if you put this quantity theta in Zin, what do you get? You get Zin becomes equal to Z1 times ZL plus JZ1 tan pi f by 2 f0 divided by Z1 plus JZL tan pi f by 2 f0. Right? So now looking at this junction, gamma, the reflection coefficient is what? Zn minus Z0 divided by Zn plus Z0. That is looking into the matching section. So if you substitute this, you have to substitute this big Zn quantity into gamma. So what will you get? So let me write this again. Gamma, that is looking into QWT from Z0 line. That is Zn minus Z0 divided by Zn plus Z0. So what would we get if you substitute Zn? So Zn we already know, we have written the expression previously. So what we will get is this: Z1 ZL plus JZ1 tan theta. I'm just writing theta for the time being, just not to make the expression too big, minus Z0 Z1 plus JZL tan theta divided by Z1 ZL plus JZ1 tan theta, I think so, yes, plus Z0 Z1 square, I'm sorry, Z1 plus JZL tan theta. So now if we open the brackets, what we will get is Z1 ZL plus, or let us group the real terms first, Z1 ZL minus Z0 Z1. Now if we take the imaginary terms, we will get J tan theta, Z1 and Z1 will become Z1 square minus Z0 Z1 divided by Z1 ZL plus Z0 Z1 plus J tan theta Z1 square plus Z0 ZL. Now let us not forget that this is a quarter wave transformer. So therefore Z1 is equal to Z0 ZL. So if we put this quantity vanishes. This entire imaginary term from the numerator totally vanishes. So then what can we say? If we substitute again Z1 square here as Z0 ZL, what we will get is Z1 ZL minus Z0 Z1 divided by Z1 ZL plus Z0 Z1 plus, this will become 2 Z0 ZL, so this will be J 2 Z0 ZL and theta. Is this fine? I think so, yeah. Okay, so what can we do? We can take Z1 common in the numerator. So this would become, if we take Z1 common in the numerator as well as the denominator, what we will get is ZL minus Z1 divided by, sorry, ZL minus Z0. So this will be ZL plus Z0 plus, now what we are going to have a term that is 2 Z0 ZL divided by Z1. Because if you try to take Z1 common, we have to divide this by Z1. So therefore this will be 2 Z0 ZL divided by root of Z0 ZL, that is 2 root Z0 ZL. So let's put this J2 root Z0 ZL times tan theta. Now let's put theta back to what we had derived, that is pi f by 2f0. Right? So this is what we have got. So let's rewrite this. Now let us go back to the concept of normalized impedance or normalized load impedance. Let's define small zl that's equal to zl by z0, right? So how can we put this over here? What if we divide the numerator and denominator by z0? So what we can do is, if you divide the numerator and denominator by z0, what we will get is small zl minus 1 divided by right? So now this is a complex quantity. So therefore, let us look at the magnitude of this gamma. So what's going to happen is the magnitude of gamma will be zl minus 1, because this is the real quantity, divided by the real part square plus the imaginary part square, that is 4. Now zl by z0, the root of zl by z0 when squared will become zl by z0, which is nothing but small zl times tan square pi f by 2 f0 the whole under root. I think this is what it's supposed to be. So we have got this expression. Now zl may be fixed depending on what is z0 and zl capital, and we have got f by f0, where f is the variable frequency and f0 is some constant corresponding to the length, actual fixed length of the quarter wave transformer. Now let us see how this mod gamma changes as a function of frequency. But what we are seeing is mod gamma is not just a function of frequency, it is a function of zl also. So therefore, this implies that mod gamma is a function of f and the normalized load impedance small zl. So therefore, what we will do first is we will fix some value of zl. We will fix some value of zl, then see how mod gamma is changing as a function of frequency. And then again we will take some other value of zl and then see how this quantity is changing with frequency. So therefore, let us do this. Let us draw a plot of mod gamma as a function of f by f0. This is called as normalized frequency. So remember that mod gamma is this ZL minus 1, small ZL minus 1 divided by square root of this plus 4 ZL tan square pi f by 2f0. Okay. So let us first take some case where ZL is 10. Case 1. So what would happen? If ZL is 10, the numerator will be 9 and this will be 11 square plus this tan function. Now the question is, when will this quantity become 0? This quantity will become 0 when f by f0 reaches a certain value. When f by f0 reaches a certain value. So what do you think that value is? What do you think that value is? So let us say we take the special case when f becomes equal to f0. So in that case, what's going to happen? This tan term will become tan square of pi by 2. So therefore this entire denominator will try to go to infinity. So anything divided by infinity is 0. So therefore, when f by f0 is 1, that time mod gamma will be 0 always. Any other point? Yes. If f equals 3f0. If f equals 3f0, then this will be tan of 3 pi by 2. So that is like every odd multiple of pi by 2. Even here, the mod gamma will be 0. So here it will be 0, here it will be 0. Now, let us put the special case where f is 0. That is 0 frequency. Then in that case, mod gamma will be what? ZL minus 1 divided by ZL plus 1. Because this term will now vanish. This second term. So now we need to put the value of ZL. So if ZL is 10, then mod gamma will be what? 9 by 11. And that is somewhere around 0.8, I guess. So 0.81 or so roughly, just speaking. So therefore, when f by f0 is 0, so that time this value will be 0.81. What if f is 2f0? If f is 2f0, this will be tan of pi. This will be tan of pi. So tan of pi is again 0. So if f by f0 is 2, again you will get this same expression because this term will vanish. So exactly over here you will get 0.81. So if you plot this other points using some numerical tool or calculator, you will see something of this kind. So it reaches 0 at 1, again rises to 2, then again drops down to 0 at 3. Right? This is when ZL equals 10. Now what if ZL becomes 5? If ZL is 5, now if F is again equal to F0 or 3F0, irrespective of the value of Z, the gamma will become 0. So if ZL becomes equal to 5, then at 0 and 2, mod gamma will become what? 4 by 6 or 2 by 3, which is 0.67. Let's say this is 0.67. This will again happen the maxima at 0 and 2. Like that. So this is when ZL is 5. So notice something very interesting. Irrespective of the value of ZL, the gamma will always be 0. That's the minimum. When F by F0 becomes 1 or 3 or 5 or any other odd number. Again, if you take, let us say ZL as 2, if you take ZL as 2, then this quantity would become 1 by 3. That's something like this, 0.33. So again, it will look something like this. This is when ZL becomes equal to 2. What if ZL becomes equal to 1? Then obviously this will be 0 all the time. Because it means that if the line and the load are equal, then no matter what is the frequency, the matching will always be there. So if I draw this, this is when ZL is 1. Now immediately there are some things which we can see. This is a periodic function. Means 1 means what? F is equal to F0. And 3 means F equal to 3F0. If the quarter wave transformer is able to do the matching at a frequency F0, then it will provide similar good matching at 3F0 also. And at 2F0, it will give the worst matching because the gamma is now the maximum. Maximum gamma means poor matching. Further, if the value of the normalized load impedance decreases, then the maximum value of mod gamma also decreases. What this means is, if the normalized load impedance decreases, it actually means that the characteristic impedance of the line and the load impedance are close to each other. So therefore, by default, not by default, so as a consequence of the closeness of impedance, the quarter wave transformer is able to provide a better matching. And as the value of normalized load impedance increases, that means that the line impedance and the load impedance are varying by a large amount. Then obviously they are more mismatched. So as you tend to go more and more away from the minima points, as you tend to go more and more away from the minima points, the maxima of mod gamma in such cases where normalized load impedance is high, or the line impedance and the load impedance are very wide apart, you will see that the matching will essentially worsen. You can also prove by yourself that this curve for ZL equal to 10 is also valid for 1 by 10. ZL equal to 5 is also valid for 1 by 5. ZL equal to 2 is also valid for 1 by 2. I leave this to you as an exercise, which is a very simple exercise to prove. So in this lecture, we essentially completed the transient or the time domain analysis of transmission lines, and we saw that no matter which approach you take, the quarter wave transformer must have impedance equal to the geometric mean of the main line impedance and the load impedance in order to minimize the reflection coefficient. And thereafter, we actually found out the frequency response of the quarter wave transformer. That is, we plotted the magnitude of its reflection coefficient as a function of frequency, and we saw some very interesting properties. So we shall continue this discussion on the frequency response of the QWT in the next lecture. Thank you.